Hi, this is ET 370, Lecture 12, Part B. This is the second part of a two-part lecture where we will talk about floating point numbers. We'll introduce floating point. It's a special type of data type for representing numbers, and we'll go over how to convert from float to decimal and from decimal back to float. And we look at a few issues, but let's introduce this floating point data type. So what are some benefits? Well, it can represent decimal fraction, and it can represent a large data range, and it can represent positive and negative numbers, right? So this is a really nice data type. Now, how does it do it? Well, it utilizes scientific notation to float, quote unquote, the radix, right? And what's the radix again? It's the decimal point, right? So if you can float that around, you can imagine you can get a large data range, okay? And so how does it work? Well, you have the sign, which is going to allow you to a bit reserved for the sign, which is going to let us to tell if it's a positive or negative number. We're going to have the significand or the mantissa, right? And then you're going to have a base to some exponent. And so this allows us to have a lot of range, and this is going to give us the precision of the number. Now we have two main types. We have single and double precision. Now we've been dealing with single precision in Arduino, which is the Arduino float or double, and it's 32 bits or 4 bytes. Okay, one bit is going to be reserved for the sign, 8 is going to be reserved for this exponent, and 23 for the significand, right? Now, if you're using double precision, like in some of these modern computers, now you have 64 bits available to you, right? Double the amount of bits, and 1 is going to be reserved for the sign bit, 11 reserved for the exponent bit, and 52 for the precision, right? So much more precision. Okay, so let's just concentrate our efforts on a 32-bit version, right? Okay, so let's say I have 32 bits, right? So I have 1, 2, 3, 4 bytes. And you can see I have the least significant bit way over here and the most significant bit way over there, okay? And you can see I have 1 bit. This is going to be reserved for the sign. The next 8 will be reserved for the exponent. And the next 23 will be reserved for the significand. That's how it's all broken up, right? And 1 plus 8 plus 23 should be 32. Okay, now it's a little bit more complicated. You know, learning is the diminishing of lies, right? That's a quote from one of my favorite professors. And really it's this, right? You have this little bias here, this minus 127, right? I'll even call this little bias, all right? And so what do we have here? We have the sign, the significand, times 2 to the e minus 127. Why 2? Because we are in base 2, right? So how is this broken out? How does this work? Well, here's the equation for it. I know, like, I look at this equation, my eyes start, glossing over, like, what the heck is going on, right? Well, let me parse this out slowly, okay? Let's look at this, the sign bit, minus 1 to this number, okay? We look at this, 1 plus summation of this significand stuff times 2 to the minus 1. Okay, and I'll go through this slowly, right? But this is just going to be an addition of one of these bits times 2 to the minus 1, one of these bits times 2 to the minus 2, one of these bits times 2 to the minus 3. And I'll work through this, but it actually isn't that bad. And then this is 2 to whatever number this ends up being in binary, minus 127. Okay, so this we'll call the total exponent. This will just be E. All right, so let's break this out a little bit more carefully. All right, so the sign bit can either be 0 or 1. If it's 0, that means the sign is positive, right? So and can you imagine negative 1 to the 0 is just 1, good, positive. If you have negative 1 to the 1, it's negative 1 still, yeah. Okay, now what about the significand? Like I said, it's actually not that bad. I know mathematically we use the sigma and all this notation to kind of write things compactly, but really is this 1 plus, let's say, what do we have? I equals 1 to 23. If I is 1, it's like a for loop, right? 23 minus 1, that's 22, good. And 2 to the minus 1, okay? Now I increments. I is 2, so 23 minus 2 is 21, good. 2 to the minus 2, good. And I is 3, what do we have? 23 minus 3, that's B20. 2 to the minus 3. So what is it doing? You're taking B22, you're taking this first bit multiplied by 2 to the minus 1, plus the next bit times 2 to the minus 2, plus the next bit plus 2 times 2 to the minus 3. Not so bad. And you just keep going all the way down to there. Okay. And so what does that mean? That means the range of this, right, because these are just ones and zeros, will end up being at minimum 1 and at most 2, right, or very close to it. Okay, and you could actually punch that in your calculator. If you just did 1 times 2 to the minus 1 plus 1 times 2 to the minus 2 plus 1 times 2 to the minus 3, all the way up to the 2 to the minus 23, and you added 1, you'd get something very close to 2. Now, if all these are 0, you're just left with 1. So that's the significand. It's a number between essentially 1 and 2. This is just your sign bit, okay? Now, what about the total exponent up here? Well, the total exponent, we know E is 8 bits, so what does that mean? This number can go from 0 to 255, okay? And if I take this number minus 127, that means my range is all the way down to minus 127 if this is 0, and it can be as large as 128. 255 minus 127 is 128. Okay, so it's still 256 numbers, 8 bits, but it's kind of going negative to positive. It's very similar to 2's complement that we talked about in the last lecture, but it's not quite the same, right? Remember, 2's complement has the invert plus 1, and then also it's kind of flipped here. The 2's complement would go to 127, and the negative would go to negative 128. Okay, so that 127, this one is a bias. All right. Okay, let's see an example of how do we represent the number 1. Okay, so if we were given a binary, we want to see what is the binary number to represent number 1 in base 10. Okay, and I'm going to tell you right off the bat, it's not just 0, 0, 0, 0, 0, 1. It's this. Gross. What is that? 0, 0, 1, 1, 1, 1, 1, 1, 1, and then all zeros. This is your floating point representation of the decimal number 1. Kind of crazy, right? But that's what it takes. This is the machinery that's needed to allow us to handle simple numbers and complicated, high range numbers, right? So we have the sign, the exponent, and all the significant values or significand values are 0. So let's check the value. Let's just see, how do we get to that 1? Well, the sign bit, that was easy. So the sign bit, it's 0 here. So we know it's a positive number, right? Good. So check, right? Now, what about the significand? Well, look at this. 1 plus, well, if all these are zeros, it's just going to be 0, 0, 0, 0. So you're just going to be left with 1 for the significand, right? And let me just pull up our little equation here just so that you can see it. This guy here. So this is 0. This is 1. Good. And then we're going to take times 2 to the something, right? Well, what is that 2 to the something? Okay, so the value here is x minus 127. So this exponent part is what? 0, 1, 1, 1, 1, 1, 1, 1. Okay, what is that number? That's actually equal to 127 if you converted this to base 10. And what's an easy way to see that? Well, by the way, if I just added 1 to that, what do I get? I get 1, 0, 0, 0, 0, 0, 0, 0. So this is the 1's place, 2's place, 4's place, 8's place, 16, 32, 64, 128. If I take 1 away from 128, I get 127. Good. So 127 minus the bias is 0. So this is actually 2 to the 0, right? So 2 to the 0. So the value is positive from the sign, 1 from the significand, and 2 to the 0 from this exponent, right? So I hope you can see that this kind of crazy monstrosity here is equivalent to our base 10 1. So yes, I showed you a little bit of a crazy case, but now let's see where else can it be used, right? Okay, so let's just see, well, what value you're going to get from this random set of binary numbers. Let's just see. Okay, so again, sign, exponent, significand. All right, and let's pull back this little page here. Sign bit, I see a 1 here, therefore it's going to be a negative number. Good. Okay, now the significand here, we're going to follow this procedure. I'm taking 1 no matter what. So I'm going to say 1 plus, and then look at this, 2 to the minus 1, right? So I've got to be right there, 2 to the minus 1, 2 to the minus 2, 2 to the minus 3, but then I got a 0, 2 to the minus 5, 2 to the minus 6, and it looks like the rest are zeros. So that's easy. I can punch that in my calculator, and I would get 1.921875. Okay, that's no problem. That's going to be this part here, significand, and now I got to do this exponent, 2 to the e minus 127. So what's e? E is 1 all the way 1, 1. Okay, good. So what's this? Well, I remember this is 128, and this looks like 1 and 1. That's 3, so that's 131, right? Okay, good. So I take 131 minus 127, and I get a total of 4. So what is this going to be? It's going to be negative the significand times 2 to the 4. Okay, I hope you're seeing this is not so bad, a little complicated, but not so bad. And the number I get is negative 30.75 base 10. So notice how this is representing a negative number and a decimal fraction. So that's a negative decimal fraction. That's what actually that is. Okay, good. We'll come back to this number. We'll come back to this, and we're going to start at this and go back to there. Okay. Okay, now let's look at the largest positive number that we can represent. So the largest positive number that we can represent is actually this number right here. 0, all ones and a 0 here for the exponent, and then all ones for the significand. Okay, let's see how that works out. By the way, if I have all ones and a 0 at the last point, this is 254, right? Because if you had all ones for 8 bits, it's 255, right? Now I see that this is 0 here, right? For the sign bit, so that's a positive 1. And now we have the significand. So now we get an opportunity to do this 1 plus, 2 to the minus 1 plus 2 to the minus 2 all the way to 2 to the minus 3, right? So if you do that, like I said, you're going to get something very large, or not very large, very close to 2, 1.9999, right? It's pretty darn close. And what is this? This is e to the or e minus 127, or 254 minus 127, and then you take 2 and raise it to that value. So 254 minus 127 is 127. Okay, so what do we get? Positive this value, which is close to 2, times 2 to the 127. Notice this is going to be a very large number, right? And we get this craziness, 3.4028 blah 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 times 10 to the 38 in our base 10 representation. So this is huge, right? What is the 10 to the 38? What's even the Google? I don't know, like not Google. That's I don't even know the word for this, right? Times 10 to the 38. Okay, how would I get the negative number? Oh, I flipped the bit, right? I would just change that bit to a 1 to represent the smallest negative number, right? Okay, now maybe your burning question is, why not just use all of the ones here, right, in your exponent? Wouldn't you get a larger number here? And yes, you would, but we reserve this special for infinity, so sometimes you have like a divide by 0 or some kind of weird kind of situation. We have a way of representing that now, right? Okay, so we go, oh, okay, well, we can't represent everything, but we can represent something that like doesn't make sense. Okay, mathematically for a computer. Okay, now let's go backwards. Let's go back to this example here, but let's start from here and work our way back and see how do we start at decimal and get to float. And I'm going to show this by example. There's a bunch of rules to it, right? Just kind of like similar to decimal to binary conversion in the last lecture, but let's just look at how we do this. So let's break this down. I have minus 30.75 base 10. Okay, and just some notation or some syntax, I guess. I don't know, how would you call this? Some nomenclature, maybe that's the best word, is this term before the radix, and the radix is the decimal point, is we call this the integral or the integer of this number, right? And this is the fractional or fraction of the number. And I think that makes sense, okay? And now we want to convert this to our floating point. So the first thing, the easiest thing, is just to get the sign bit. And we see that it's negative. So since it's negative, the sign bit will be 1, right? We're kind of doing the reverse of this. If we see the sign, then we can get the bit. So we know that the sign bit is going to be 1 here. Good. Then we got to convert the integral, or the non-fractional part, to binary. Okay, so how do we do that? We go 30. Well, how do we break this down? We can do that same divide by 2, keep track of the remainder, right? Let's do it. 30 divided by 2 is 15, remainder 0. Good. 15 divided by 2 is 7, remainder 1. Good. 7 divided by 2 is 3, remainder 1. 3 divided by 2 is 1, remainder 1. And 1 divided by 2 is 0, remainder 1. And we're going to stop here because we got a 0. the list from last to first is our binary number. And we could double check. Ones place. So this, what do we have here? We have 1, 2, 4, 8, and 16. Is that right? So if we add up these numbers here, we should get 30. Is that true? So let's double check. I think so, right? Because we got 16 plus 12 here plus 2, right? And then this is 14 plus 16, and then this is 30. Good. Okay. Okay. So we've converted this to binary. We're going to hold on to that number. Okay, what's the next step? The next step is we're going to convert the fraction to binary, and we're going to hold on to that number. Okay, so how do we do the fraction? Well, remember, if we have a fractional part, we have to multiply by 2. Okay, all right, so what do we do? 0.75 times 2 is 1.5. Take the fractional part, 0.5 times 2, we get 1.0. And we stop here, and we keep track of the ones place. So we get .11 is going to be our fractional part. And does that make sense? So if we have 0.11, remember this is the halves place and this is the quarter place, right? And if we take a half plus a quarter, we get 3/4, which is 0.75. Yes, so that seems like it makes sense. Okay, so we have the, what do we have? We have the integral part or the integer part, and we have the fractional part. Good, and we'll just hold on to those. Now we're going to combine them both. Okay, so, and then we're going to what we call normalize with base 2. And you'll see what I mean. That's why I want to do this through an example. Okay, so I'm going to take 1110.11. So I'm just smashing both of these together. Good. And which is going to be the same as, notice I have 1, 2, 3, 4 dots to get this normalized so that there's only a ones place, which means I got to multiply this by 2 to the 4, just like we do for scientific notation base 10, right? Okay. So I have 1.111011 times 2 to the 4. It's the same as this, right? These are equivalent. Okay, now what's going to happen is we need the binary fractional part, and we need this exponent part. Remember, this is looking very close to our answer, right? So what do we got here? Well, the binary fractional part, this is going to be related to our significand, and this is going to be related. This is our total exponent 4. Okay, so how do we get our total exponent? Well, we actually need to take this and add 127 to get E, right? So if we go back to our formula, let's go back to our formula here. The total exponent is E minus 127. So E is equal to the total exponent plus 127. Good. So that means our E is 131. Fantastic. That's exactly what we were predicting before, 131. Good. And we can convert it to binary. So we get 131 is 10000011. And again, we can check 128 plus 2 plus 1, 3. And look at that. Is that following that E? Yep. 100000011. Good. Okay. And what about for the significand? Well, the significand, well, that's just straight up what it's going to be. 111011. That's great. Is that correct? Yes, 111011. Done. We have the significand already in place, directly written. Okay, just by normalizing it, we get it. So that's nice. And now we're going to take our answers and smush them together. So what are our answers? The sign bit, the exponent, which is 10000011, and the significand, and just smush them. And so how do we smush them? Just like this, right? Sign bit, exponent bits, significand bits, and that means negative 30.75 is this, right? And that should match our answer from before, okay? So I hope this example highlights how to go back and forth between floating point and decimal. Now, the last thing I do want to highlight is some issues with float, right? So since you have all this machinery in place, the computation is slower, okay? And so sometimes exact numbers are impossible. And we talked about that. Remember 0.7 from the last lecture in lecture 11? 0.7, if you keep on, you're going to get that repeating pattern. It's the same thing here. If you try to represent 0.7 or some special integers, binary just can't do it, right? And floating point just can't do it. So if you're going to check a binary number, let's say you want to check if some number is greater than some tolerance, you want to use greater than or equal to or less than or equal to. You don't want to use equals equals. For example, if you have the if statement, if the variable equals 0.7, that might fail on you even if it gets pretty darn close, because it might be 0.7000003, something like that. And it might not ping your little check. So if you do this, it's going to be much more robust. Okay. Another issue with floating point is going to be the limitation on the precision, right? And so, for example, if you have this number, you might think, oh, that's totally within range. I should be able to represent that. Sort of, but you might get truncated in terms of your precision because it can only store a certain amount of significant figures, even though this number is less than the max. Okay. All right. Well, thank you for paying attention, and we will see you in the next one. Hope you learned a lot. Have a great day.